All right, and we're here. So this will be the 8.1 lecture. And again, like I was saying on the message, I'm really sorry, guys. Basically all the Zoom sessions I had to give for the other online class I have, I kind of couldn't not do those this week, as well as the office hours. Oftentimes when I'm doing these videos actually is during my office hours because I don't have a ton of students coming by right now, or hadn't had a ton of students coming by. But now people are coming by. And so anyways, so I tried to get this, at least this video done, and just didn't have a moment, but we'll get it done today. And like I said, hopefully you already looked at it and honestly tried the homework, because this stuff is actually, this section in particular is really easy. So I wanted to just get this done, knock it out. This is Sunday right now. So get it done, knock it out by the end of the night. It'll be really easy. And then we can focus on 8.2 and 8.3 next week, because those will take a second to kind of look through. All right, so let's look at the reading. And actually, I think for this section, because it's so easy, the way I set it up basically is I'm only going to do the reading questions. I don't even need to do any extra questions. So let's just start the reading questions. I started y'all off with 3, C, and D. So in this chapter, we're looking at relations. So we looked at sets to begin with in chapter 6, and then using sets, we were able to talk about functions. Again, something that you were well familiar with, but we talked about it in this more sort of abstract sense. Something else that you saw maybe at the beginning of a college algebra class and then never saw it after that is relations. And the reason you don't see it after that is because in algebra, pre-calculus, calculus, we are studying functions. So we tell you about relations to begin with, and then we're like, oh, but we want these special type of relations called functions, and we're only going to study those for the rest of your practical math career. However, relations, so what we want to do in this today and in this chapter is we want to go back to relations, because relations are actually hugely useful. So functions are nice because with functions, we know that every input only has, what do you call it? Yeah, there's no repeat. Basically, every input only has one output. So if I pick a value in the domain or whatever, if I put in a number to that function, I'm only going to get one thing out of it. That's a nice kind of cause and effect type scenario. And so we focus on functions in most of mathematics because that type of cause and effect type scenarios, basically that's the basis of how we do the scientific method. When we set up an experiment, we do all that kind of stuff. We're changing some input and we're looking at what's the change in my output. And so we study functions because it matches the way that we know how to study the world well, the scientific method, at least the physical world. But also because they're kind of easy to deal with. So once you have that restriction that every input only has one output, doesn't have to be a one-to-one function, just a function. Every input only has one output. So the predictability of if I do this, I get this. That's actually kind of easy to study, relatively. And it's easy to think about, and it's an easy way to kind of frame our world, right? So if I do this, I only ever get this. However, my question to you guys is the world, is the universe, people, Earth, whatever, however, whatever domain you want to break it down into, is the world, the universe only that way? That when you do something, you only ever get one. When I do A, I only ever get one result out of it. Good. That unfortunately is not how the world works. Some would say that maybe we just don't know all the variables, right? But actually I think there's plenty of examples in our world of of things where you do an action and you get multiple different outputs. And it's not based on the other variables, it's just the way the thing works, right? So we would like the world to be functional. We would like it to be, if I do this, I always get this. Unfortunately, that's not how the world works. And so for the physical world that we like to study, we can study a lot of it well enough using functions, but we actually can't study all of it. And so that's actually one of the reasons that we have, I would say not the reasons they invented statistics, but it's one of the reasons that statistics is so useful. Statistics is a math about, when I do input A, I'm looking at what's the probability that I get this output or this output or this output or this output. So statistics automatically studies things that are not functional. And we're looking at some sort of probability distribution that when I do A, I get one of several responses out of it, right? So statistics naturally helps us deal with studying things that are not functional. So statistics ends up being used for a ton of, for sociology, psychology, even economics, a ton of things that we deal with in life that especially that involve people are not functional. You do thing A to person B, and sometimes you get response C, and sometimes you get response D. And it's again, it's not because you didn't, you did the exact same thing, and it's not always because they're they have a different mood that day. It's just because we're not functional. So that's sort of a big introduction to the idea of, so we're going to back up from functions and look at relations. And again, relations allow us the possibility of, if I do thing A, I have several possible results that come out of it. So we are going to lose that restriction that if I do one, if I pick an X, I always get one Y value out of it. And that's basically what a relation is. So a relation in general is just, it is just a set of ordered pairs. It is a gaggle of ordered pairs that tells me the relation between things in my domain and my codomain. So you'll see kind of the vocabulary we're going to keep using. It still uses the same vocabulary as a function. You're still going to have a domain. You're still going to have a codomain. You're still going to have images of things. You can even write it sort of using functional notation. The difference is basically functions are a subset of relations. Relations are actually the broader idea, because we are losing that restriction that we have with functions. We're losing the restriction that every input only has one output. So now if I pick a value in my domain, it could be related. It could cause as many other possibilities in my codomain as I want. It's all good. So let's look at we'll do these first several reading problems are just to get you used to, which things are related to which using using some relation. You'll notice the relations are going to be defined exactly like a function. Or similar at least. So relations they're a function without the restrictions that we put on functions. So they're kind of a super function. Yeah, but let's look at it. So like I said, I think what did I give you? 3 C and D. So let's look at 3 C and D. So in 3 though, let's make sure. In 3 though, we're using this particular relation. They call it the congruence modulo 3 relation. So let me put some of the words down here. So congruence mod 3. T. And this relation goes from Z to Z. So again, you'll notice the notation, everything is exactly like we have for functions, because functions are a subset of relations. So basically functions are relations. They're relations with an extra restriction that every input can only have one output. So all of our vocab, all of our notations are going to be exactly the same. We just lose that restriction. Now every input could have as many outputs as we want. So congruence mod 3. So I'm gonna show that relation using T. The domain is integers. The codomain is integers as well. And for part C, sorry. Again, before I write that, and then the way that we show this relation, or we figure out this relation. So M is, so the way you want to read that is M is related to N mod 3. So M and N are connected to each other, related to each other, if and only if. So notice they're using that if and only if from chapter 2. 3 divides M minus N. Now, this is an alternative way to do modular arithmetic. So I noticed you guys actually used a lot of modular arithmetic on the 6.1 homework. I started going through grading those. I want to come back to a note on that, but just when we do the review, you can't really use modular arithmetic to prove that things are in sets. So just really quick, let's just take a break from this for me to just say, going back to that that 6.1 homework, you were trying to prove that an element was part of a set, but a lot of y'all made the argument essentially of, oh, these have the same result mod, whatever it was, mod 16 or mod 18. Therefore, they have to be the same as each other. And if you're going to make that argument, one, you have to be very rigorous about that argument. So you have to show me that they actually, you can't just say that they have the same result mod whatever, mod 3, mod 18. You need to show me with some algebra. And then you also need to show me that basically the element you're looking at is still an integer. Because the reason is those sets were defined using basically arithmetic or really divisibility. They're really defined using divisibility notation. And so you had to prove things according to the definition of divisibility. Or using, kind of using algebra. And so a lot of people, unfortunately, on that homework, you didn't do that. So if you used the mod, I think there was only one or two people out of the maybe, I think there was like six. I don't know, there's quite a few of y'all, it's more than six probably, but I think there was quite a few of y'all that used modular arithmetic as a way to argue it. And because it's in the class, I'm not saying that it doesn't work, but you guys were very loose about it. You just kind of said, oh, it fits. It's this mod 18. And I need to see the algebra on that. Basically, if you're going to use that, then you got to use the definition of modular arithmetic and show me. So you guys had a good idea. You just didn't go far enough with it. So I think there was only two of y'all that actually kind of did everything you needed with modular arithmetic. So in general, on a problem like that, though, so going back to chapter 6, so this is again nothing to do with what we're about to do, but going back to chapter 6, if you're going to prove an element is in a set, you really need to use the definition of the set. The definition of those sets was, what, 18t minus 2 or something like that. So you really needed to start with that and not try to do kind of a slick argument with modular arithmetic. Again, it's not that it's impossible, but the modular arithmetic is actually a harder argument to make because you have to make sure you have to show me all the algebra. You have to show me the modular calculation, and you have to prove that things are integers. So anyways, so just a caution there for you guys, since we're seeing modular, I was reminded of it because we're seeing modular arithmetic, but a caution there. So, and when we go to the review for this final, that's going to be chapters 6, 7, and 8, then we'll talk about that again. So sorry. But this is an alternative way to do modular arithmetic. One way to define modular arithmetic is you divide by whatever in this case, mod 3, and you divide by 3 and you look for the remainder. And so you can algebraically kind of show the reader, this is what we're looking at. Another way to define it, though, is two things that are equal. So again, going back to the argument you guys were trying to make in chapter 6 by saying that two elements have the same, their remainder is the same, mod whatever. So if you think about it on a number line, let's say, so we're doing mod 3. So let's say we're looking at like 5 and 5 mod 3. So kind of walk with me through this. So if I've got the number 5 and I'm doing 5 mod 3, what is 5 mod 3? Good, that's 2. So you divide by 3, goes in once with a remainder of 2, so your mod number there is 2. So let's pick another that's that. So like 8 is another one. That is, if you divide it by 3, it's going to go in twice with a remainder of 2. So both the number 5 and the number 8 are actually 2's when you look at a mod 3. Notice that 8 minus 5, what is 8 minus 5? It's a 3. And so those two, in some ways, you wouldn't. Another way to know that they're the same mod 3 is just to know that they're 3 apart. Because if they're 3 apart, they have to have the same remainder. So you can even think about this like on a number line. So let's say, let me just get a number line going. 1, 2, 3, 4. So this is the number line of integers, but then when I count it mod 3. So mod 3, this is a 0, and that's a 1, and that's a 2. But then 3 is a 0, and 4 is a 1. And like we said, 5 is a 2. So we're just looking at their remainder after you divide by 3. And then 6 is a 0, and 7 is a 1, and 8 is a 2. So notice that you're just repeating the same, you're getting the same remainder every 3 numbers. So another way to define modular arithmetic instead of trying to define it using algebra and the remainder is you can just say, let me subtract the 2 numbers and see if they're 3 apart, or they're a multiple of 3 apart at least. So again, even like 2 and 8 are the same mod 3, and they're 6 apart, but 6 is a multiple of 3. So again, anytime you're doing modular arithmetic, it should be natural that if you're a multiple of whatever your mod number is apart, then you know those remainders have to be the same. So this is the definition they're going to use in this section. When we talk about it though, so you can think about it that way, or you can just think about it using remainders. I personally still like to use remainders when I talk about and think about modular arithmetic because I think it's quicker for me, basically. It's quicker for me to just divide and figure out the remainder than to figure out does 3 divide into the difference of the 2. It just seems like a bit more work. So anyways, let's finally get to the problem here. So part C here, they want you to list 5 integers n such that n is the same as 1 mod 3 or is related to 1 mod 3. So 5 different numbers that n could be that have the same remainder as 1 does using t, which is the mod 3 relation. And so what did you guys have? So some numbers you might have had. So again, 1 has a remainder of 1. So does 4. So does 7. So there's at least 2 numbers there. And you can keep going. So maybe you just did a bunch of positive numbers that all, when you divided by 3, had a remainder of 1. So that means what? The next one would be a 10. But we can also do some negative numbers. So the fun thing about this number line is we can do the counting backwards just as well as we can do it forwards. So this is -1, -2, -3. So again, these are the integer versions of the numbers. But then mod 3, when you're looking at their remainders, so -1 actually has a remainder of 2. So you would think it's 1, but you want to think about, so again, our base definition for modular arithmetic. So if I'm doing mod 3 is I divide by 3 and I look at the remainder. So when you take -1 and divide it by 3, the problem is the closest integer that's divisible by 3 is not to your right, it's actually to the left, it's -3. So -1 would equal 3 times -1. And then that gives you the -3. And then you're looking at what the remainder is. The remainder is just the distance from -3 to -1, and that's going to be +2. So your remainder, your mod 3 for -1 is actually +2. And again, if you look at the numbers mod 3, using the pattern, it can't be anything but a 2 because our pattern is a 0, a 1, a 2, and then a 0, a 1, and a 2, and then a 0, a 1, and a 2, and it keeps going that way. So that means -2 is going to be a 1 because again, -3 times -1 is -3, and then my remainder is +1 there. And then -3 though is going to be a 0. I can divide that by 3 evenly. 3 times -1 plus 0. Etc. So that means this would also, -4 would be, mod 3 would be a 2. -5 would be a 1. -6 would be a 0. And that gives us a couple others. So again, I mean, they said list 5 integers. I mean, if you think about it, there's an infinite number of numbers that are going to be the same as 1 mod 3. Because you can keep going on the number line. So you didn't have to list the same 5 that everybody else did. Or that anybody else did. You just have to list 5 numbers that are indeed a remainder of 1 after you divide by 3. So you could have listed more positives. I'm going to list some of these negatives. So remainder of 1, that was also -2, and that was also -5. And you could keep going negative, keep going positive, all of those work. And then the same for D then. So D, they wanted you to list 5 integers n such that n, so we need n mod 3 to be the same as 2 mod 3. And again, there's a bunch of them. But 2 mod 3 has a remainder of 2. So some others that I could use here is 5. I could use 8. I could use -1. I could use -4. Whatever you want to do. I guess I'll go one more positive. So what, 11? Good. And your homework is, like I said, so on this one, literally the homework is just mirror questions of the reading questions. And so you'll have some like that. I also had you do 5B and C. Let me see if there's any more interesting things that I need you to do there. So let's look at 5B and C. In 5, I was getting you to look at this idea of power sets again against subsets of the larger set. So let's look at that. So in this problem, first of all, there's a large set, and there's a larger set we're dealing with. It's actually not that large, but set is ABC, and then P of X is the power set of X. It is the set of all subsets. So we're going to define a relation S on P of X as follows. So kind of like the last one, so S, they didn't write it here, but basically what we're saying is S is going to go from P of X to P of X, large X. So my domain and codomain are going to be the subsets of X, all possible subsets. And the way this relation works is A is related to B, or if I put in A, I can get out B if and only if A has the same number of elements as B. At some point in, I think that chapter 6, she mentioned that there's actually a word for, we've been writing has the same number of elements or the number of elements in a set. There's a word for that. They call it cardinality. And yeah, but I think so you could say the cardinality, but if that sounds like a weird word, then all we're really trying to say is A has the same number of elements as B. So then, I think I gave you guys B and C here. So basically, B is asking, is this subset related to this subset using that relation? And so what did you guys say? Good. That would be a no because this has 1 element, this has 2 elements. So to answer this, you could say no. You could also say, basically put a slash through. So another way to answer this is you could say A is not related to B, comma C, kind of like we say, an element is not in a set, or we say, yeah, just with the slash that we've been using for a lot of those cases where we need to say not in. So you could say something like that, or you could just say no. They are asking a question. And then C, though, we have the subset C, and I'm asking the question, is it related to B? And y'all say, good, yes. Or you could just basically retype that. Easy enough. Well, that's what I mean. This section is just, since it's introducing relations, this section is just kind of, can you orient yourself, read them, figure out which things are related to each other? Just can you do the basic things of a relation, which is which inputs are related to which outputs. See it. Eight, we had an example using strings, in this case, A's and B's. So A is going to be the set of all strings of A's and B's of length 4. So we're specifically locking ourselves down to strings that have that are of length 4. Define a relation R on A as follows. So this relation goes from A to A. We input a string and we output, or we want to figure out, is another string related to it? Is it an output? And the way this works, so I guess they're saying here, so for S, E, and A, S then is related to T if and only if they have the same first two characters. So S has the same first two characters. Same. So basically they have to have same first two characters. And if they are, then we say they're related to each other. So again, whenever we give these computers examples, I don't know if you've noticed, I've started asking you, okay, like what might this be good for? You know, so again, I promise you, she's not bringing these examples out of her butt. Basically, she's not just sort of, like, I mean, I don't know, maybe a couple of these are, but I promise you, she's not doing that. The author has, has a lot of what do you call it? A lot of history, research, like kind of time spent with computers. So she's really bringing this out of her knowledge on things that might be useful, basically. And, what do you call it? In computer architecture, computer construction, etc. So it might be, so the question is, this relation, before we answer questions, what might it be useful for, right? And what do you guys think? And again, without hearing your responses, this is a lot better when I have at least even just a remote class so people can talk. But this might be good as, again, a kind of a classifying schemes for strings. So maybe there's a good reason why the strings that we're receiving, maybe for a particular function, a particular program, maybe the first two letters of those strings are used basically to route the strings to one place or another. They're used in some way to classify those strings as letters or strings that have a certain purpose. So maybe it's useful then to classify these strings by their first two and then basically program that into some base piece of hardware as a way to sort the strings when they're coming in so that they can be used for a certain purpose. So maybe something like that. But the questions I gave you on this one, did I just give? Yeah, just to give. So I gave you just C and D on this. So is a related to, sorry, um, B. And what's the answer there? Yes. They both have double A to begin with, so we're good. And then part D. I remember last semester, this was actually an interesting question to go over this particular part. So B, A, triple A, is that related to A, B, A? This is an interesting question to go over because several people kind of pointed out, well, does the order matter? So basically, you have BA to begin the first string and AB to begin the second string. And at least without any context, we actually kind of don't know. But I think we can read her intention. I think I can sort of read her intention here. Just also with some practical knowledge about computers and how they work, computer hardware, chips and how they work. So what was your guys' answer here? Are these related or not? And hopefully, so that it should be no. Like I said, there's nothing about the context that really tells you whether the order should matter or not. But if you think about how computers work and stuff like that, I mean, the strings are read, whether it's right to left or left to right, but they're read one bit at a time, right? So it is going to matter to whatever piece of hardware is receiving this that it sees a B first and an A second, as opposed to an A first and a B second. So this should be a no. Good. All right. Again, just simple stuff. Identify whether things are related to each other. Let's look at 10, see 10, 13, and 15. So 10, 13, and 15 is where we start to get to have some fun with this, because now we're gonna sort of, again, we can always state a relation, like we can state a function this way, and this is a very compact and nice way to state it because it tells you exactly what things are related to each other and not, and why. So we can, again, like this, they ask you, is this one related to the other? Yay or nay, and you can say it because your head can figure it out. You can, this is exactly what you need to figure that out. However, it doesn't tell you, so if I kind of asked you what is the whole relation? So a relation is a set of ordered pairs, and we use our ordered pairs to just show what input is related to what output. So if a relation is just a gaggle of ordered pairs, if I ask you what the relation is, this tells you what things are related to each other, and we use it symbolically as a stand-in for the relation, but it's not the relation. That is not, I have not listed all the ordered pairs for you. You don't know all the things that are related to all the other things, but we know how to determine which ones are part of the relation. But there's a fine kind of tune or just fine difference there between this R. The way I've described it is enough for me to figure out what's in the relation, and I use it as a stand-in for the relation, but it is not actually the relation. It is not the list of all inputs from the domain paired with outputs from the codomain that are related to each other. Now, on some relations, it would be either impossible or nearly impossible, practically impossible to write all those out. But on some relations, we can do that. So that's what 10, 13, and 15 are about, ways that we can write out this whole relation. Show all of the elements that are actually related to each other. So let's look at 10. So on 10, we need some background info. So A is the set 3, 4, 5. B is the set 4, 5, 6. And R is going to be what we call the less than relation. So R is a relation from actually A cross B. So let's see. hold on, is it, oh, did she? Is it ordered pairs that we're relating? Yeah, actually, no, sorry, I mean, I think the way she said it is fine, but. So R is gonna be a relation from A to B. But R is our less than relation, so what we're saying is X is less than or related to Y, so X is less than Y. Or X and Y. X and Y are gonna be, or yeah, that. Okay, words are failing me right now, but basically what we gotta check is X less than Y, so we're gonna pick an element for from our domain, pick an element for a codomain, and if X is less than Y, then we pair them up and we call them, and we say that they're related to each other. So this is just a very weirdly fancy way of basically saying we're doing less than. So what she wanted you to do, what I want you to do in this one is state explicitly which order pairs are in R and which are in R inverse. So this, again, this is tells me how to do the relation, but the relation itself is a set of all the order pairs we could get that fit this, where X is less than Y. So what did you guys get? So let's start with the 3. So if I pick the 3 from A, which elements from B is 3 less than? Good, it's actually all of them. 3 is less than 4, it's less than 5, less than 6. So again, the difference, notice I'm gonna get 3, 4. My relation, because 3 is less than 4, I'm gonna get 3, 5. And I'm gonna get 3, 6. So again, notice that my input has multiple outputs. And again, that's the whole difference between a relation and a function. Can have multiple outputs. Let's then go to the 4. So which of these numbers in B is 4 less than? Good, now it's just the 5 and the 6. So 4 is gonna be related to 5, is less than 5. 4 is less than 6. And then finally, the 5 only has one output that it's less than. 5 is less than 6. So that'll be my other order pair. And this is actually your relation R. Your relation R is the ordered pairs that fit, again, this rule. So this is really the rule of the relation, where number from A is less than a number from B. Good. And they also asked for R -1. Again, the terminology, again, going back to chapter 7, same as chapter 7, it's the inverse. So in this case, it's the inverse relation. And the inverse just means you switch it around. But the nice thing about relations is we don't have the restrictions we do with functions, and functions, we're dealing with functions. You only technically, you have an inverse, you always have an inverse, but you only have an inverse function when the function's 1-to-1. Here, again, we don't care. My inputs could have as many outputs as I want all day, every day. So because of that, I not only do I always have an inverse, I can always write an inverse. It's always there. You always have an inverse relation. And an inverse, like you guys learned way back in college algebra, you just switch your inputs and your outputs. So our inverse would be the set 4, 3, 5, 3, 6, 3, 5, 4, 6, 4, 5, 6. In this case, we can even basically not only guess, we can essentially name this relation. You can't always, but if this was the less than relation, if R was the less than relation, then when I flip it around, what do I get? But that's greater than. So this would be the greater than relation on these two sets. And there you go. So, but again, the emphasis I really try to make there is The relation is all the ordered pairs that actually show all the relations, all the inputs and outputs that meet that fit whatever the rule of the relation is. So this is my relation, and this is my inverse relation. Oh, let's look at let's then go to 13. So then 13 and 15. I like these problems because then so this is, like I said, this is my relation. But a little bit like we looked at in chapter 7, when we were looking at functions, we noticed that honestly, when the ways of giving functions, the ways we gave functions basically as an equation or as a picture, some sort of graph, or even if you just think back to college algebra, calculus, etc. When you take a function and you either graph it or you give it as an equation, it's sort of the most compact, kind of nice way to give that function. You don't have to do a ton of writing. Listing the order pairs is always a crap load of writing. And so the thing is, it's nice because it gives you every single detail you would never need. It gives you all of it. It gives you the whole thing. But I mean, if I had 20 order pairs or 100 order pairs, then visually looking at it on a page or looking at it on this board, your mind would literally just zone out. And that's not just something that we do. I don't know, that's not just a student thing. That's actually they've done some psychological research. It's something your brain does. If your brain sees the same set, like basically sets of symbols and elements over and over again, it basically treats it like it literally zones out and treats it like white noise. Like it can't differentiate between the things. So anytime we have to, in this case, show a relation, but anytime we have to show data or show something to a reader, and the way we're showing it ends up being a crap load of symbols and numbers, it's not a good way to show it to readers. And so mathematicians also know this. And so again, like I said, that's why if you think back to your algebra and calculus classes, you rarely ever wrote ordered pairs. After they told you a function used ordered pairs and and ordered pairs, you can graph them. Once you saw graphs and equations, the rest of your math was about those graphs and equations, basically. And there's a reason for that. Graphs and equations are very compact ways of giving you the same information. You do lose a little detail, but they give you the same information in a very small space. And it's also something that the brain stays actively engaged in, basically. So these next problems, 13 and 15, are about doing the same thing. So we're going to write out the relation, but we're not going to write it this way because this is, like eventually this is going to get crazy to write a crap load of ordered pairs. We would need some different ways to write out these relations. So on 13. Well, 13, we'll start there. So they say define a relation on A. When they say that, what they mean, so R, in this case, R, the relation, is going to be from A to A. So that last relation on number 10 that we looked at, the domain was A, the codomain was B. But if you look at some of the other relations we looked at before that, the domain and the codomain exactly matched each other. So I think on 8 it was the power sets. On 3 it was it was integers. So they were relating two sets of numbers that were exactly the same as each other. So you can do both. You can relate things from two completely different sets, or you can relate things that are where from the same set of numbers, where the domain and the codomain match. When they domain and codomain match, they'll often say it that way. Define a relation R on A. When they say on A, that's your cue of okay, they're taking elements of A and relating it back to elements of A. So R goes from A to A. We probably need a definition of A. So A is 0, 1, 2, 3. And here, so instead of giving you again a rule of the relation, they just give you the relation. So they're going to say the relation here, R is 0, 0, 1, 2, and 2, 2. And it's interesting when they give you the relation this way. So like in the last problem, we had to figure out what this was. But when they give this to you, the interesting thing about this is, why does 0 relate to 0? Shall not say. And do I need to know? No. I actually don't need to know why one thing is related to another. We just need to know when I put in one number, what does it stick to? What do I get out? What is it related to? So 0 is related to 0, 1 is related to 2, 2 is related to 2. Why? ¿Por qué? Está bien. No necesito conocer. Or ser. Whichever one. Yes, ser. But I just really don't need to know. But if you look back at those previous problems, all of our other problems so far, they've given you the rule of the relation. It is nice to have the rule of the relation. You know why one thing is related to another. This is also, again, why it's nice to have an equation for a function, because you know how one thing relates to another and kind of why. You know how to create it. You know, you can plug in a number, do your calculation, and it gives you a y, and you know kind of how you got there. You know, cause and effect. But ultimately, we don't actually need to know cause and effect. We just need to know what's related to another. Anyway, sorry. So they want you to draw the directed graphs. So this is not a horrible way to write this because there's not many ordered pairs, but another way that we can write this. So especially as long as your domain and codomain are the same. So another way we can do R is what's called a directed graph. So I'm gonna mark a 0 here, I'm gonna mark a 1 here, and I'll mark a 2 here. So what I'm literally gonna do is I'm gonna mark the points out. Notice that this is actually kind of like an arrow diagram that we were looking at in chapter 7. And in fact, that's actually what this is. So I actually one way to draw this. So let me do an arrow diagram first, and then I'll show you how we kind of collapse it into a directed graph. But I want you to see the arrow diagram first so you can see a directed graph is just an arrow diagram. We've just simplified the visual to it. So if I did an arrow diagram of this, so I would have A here and I would have A here. This would be 0, 1, and 2. And this would be 0, 1, and 2. And I know from my relation that 0 goes to 0. I know that 1 goes to 2, and I know that 2 goes to 2. So this is an arrow diagram of that relation. Just because you learned arrow diagrams in the functions chapter doesn't mean you can't use it for other things. Like I said, it's like I was saying in that chapter, this is actually a really crazy useful diagram in a lot of scenarios that, again, like you got taught it week 1 of a college algebra class, and then they what do you call it, never got back to it because they were majoring on getting you to graph on a Cartesian coordinate system, because for the rest of pre-cal, cal, etc., you were dealing with real numbers and you were graphing on a vertical line and a horizontal line that were real numbers. So because you were doing that, they basically, all these other diagrams, they were just like, okay, whatever, like we don't need those. But it ends up when you're not looking at things like that, when you're not looking at algebraic functions, the arrow diagram, like I said, is just hella useful. It's crazy good. So anyway, sorry. So 0 relates to 0, 1 to 2, 2 to 2. But notice that, so again, this is just an arrow diagram of that relation. But what I notice here is there's some redundancy, and it kind of sucks to write A twice and to write 0, 1, and 2 twice. So all a directed graph is I'm taking out the redundancy in this arrow diagram. So I'm writing 0, 1, and 2 once. 0 goes to 0, so I'm going to write an arrow from 0 back around to 0. But it's just an arrow. It does the same thing that the arrow diagram does, but now I just don't need to write the 0 twice. And I don't know, my arrows may be a little bit shorter, depending on how I draw this. So a little nicer, a little less work. What about 1? 1 goes to 2, so I'm going to write an arrow from 1 to 2. And then 2 goes to 2, so I'm going to write an arrow from 2 back around to itself. And voila, you have a directed graph. So this is a directed graph of the relation R, but then like, just like for R, the ordered pairs is the relation. This is the relation because it tells you the exact same thing. It tells you all the ordered pairs. So this is our relation. So a directed graph is just a arrow diagram that's been collapsed down so that you don't have to repeat what you're writing. You don't have to write the set twice and write the numbers twice. That's all it is. But it's really nice. So that was a arrow diagram. This is a directed graph. And you just have a couple problems like that where they want you to write, or I wanted you to write the directed graph. So let's do 15. This is a fun one. So on this one, so A is the set 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8. And we're going to define a relation on A. So R is going to be from A to A. And the way this relation works is that X is related to Y if and only if X divides Y. So X divides into Y. Again, we're bringing back that divisibility definition. So also wanted to bring in this problem because you're just going to keep seeing that. So all those definitions from chapter 4, I just promise you, you're going to keep seeing them over and over again. And what they want you to do here is, again, they want you to draw the directed graph of this. So again, what we're going to do is we're going to list out all these points, and then we got to go through and figure out which numbers divide into another one, so pick one and see what other numbers it divides into. And then we're going to draw arrows to show that. So doesn't matter how you organize these. I guess what I'm going to do is let's do 2. Let's do 3. Let's do 4. 5. 6. I'm trying to make these dots and not dots you're used to seeing. 6. Let's do 7. And let's do 8. So what divides into what? And so this is one that, so again, if you already did this for the reading, just kind of wait for a second, but this is actually one to really think through. So what divides into what? So I want to give you guys a second on that. So I'll pause on my side, you pause on your side if you haven't done this, and figure out which of these numbers divides into the other. All right, let's see what y'all got here. So again, I think the weird thing about this is, again, it's really as X divides into Y, which means Y equals X times an integer. So X has to, basically, the way you normally think about it, X is your factor. So X has to be a factor of Y. Well, so the first thing is everything is a factor of itself, technically, because you can divide it by itself. Again, we're using the overall definition of divisibility, which isn't restricted to the numbers in this set. So 2 times 1 is 2, that's good, that's divisible. 3 times 1 is 3, so we can do every one of these to itself. So I'm going to start there. Yeah. Something like that. So that was maybe not the tricky part, but you may not have thought of that, or maybe you did. Maybe that was like off the bat, you're like, oh, I know there's a trick here. It's there, everything can divide itself. Then the non-tricky ones. So 2 divides into a 4. 2 times 2 is 4. 2 divides into a 6. And 2 divides into an 8. So we're going to have those 3 arrows. And then I'll go to the 3. 3 divides into a 6. But then we don't have anything else in the set that it divides into. 4 divides into an 8. And then everything else doesn't divide into anything higher. So 5 doesn't divide into any of those, 6 doesn't divide into those two, 7 doesn't divide into 8, etc. So this would be the directed graph of that relation. Good. So again, a visual way to represent this, that especially when we start getting a lot of, like if you actually wrote this out, when we start getting a lot of ordered pairs, this is a much better way to see it. Your mind sees it and instantly exactly knows which ones are related to each other. Again, just like when we give a rule or an equation for a function or a relation, your mind can think through it and know exactly which ones are paired with each other. You just gotta do a little thinking through it. So those graphs and rules or equations are always better ways for our mind to see functions, relations, etc. So yeah, just lots of information very immediately in a small space. So relatively small space. All right, good stuff. But that is this section. So I'll put that up. Go ahead and knock out that homework. And yeah, and I'll see you guys for the next two.